Well, here we are. We're up to day 6 for chapter 2 for circular motion, and it's our first of 2 days looking at orbits. Last day we were reviewing gravity force, and now we can use that knowledge to help us figure out how planet orbits work. So planets are actually a nice application of what's pretty much circular motion. Turns out today I'm going to lie to you a little bit on this lesson, but don't worry, I will correct all of those lies in the next lesson. So there are some small lies. I'm crossing my fingers as I say some of the things that I'm about to say here, but we will fix it up by the time we've done the next lesson. So I'm going to say that, yeah, the planets travel in these orbits that are nice circles. Okay, it's a bit of a lie, but it's close. And gravity is the only thing out there providing any kind of force. So gravity will be the net force. It'll be the total force. So let's just take a little picture here of the Earth, and we'll look at an orbit, maybe the moon, okay, going around the Earth. So yeah, it's pretty much a circular orbit. There's the moon in one spot in its orbit, and it has some velocity tangent to that circle going off to the side. I'm actually being a little careful here. I'm deliberately not exactly attaching this velocity vector to the moon because it's not a force, right? Just because you're going some way, that's not a force. But that is the way that it's going right now, we shall say. And there, attached to it now, okay, my little velocity vector went self-attached to the moon, but the red one there is the only force, that force of gravity. And so when I stare at it and go, okay, well, what do all those red things add up to? There's only the one force, just the force of gravity, and it's going to make that moon circulate. It's going to make it go around the corner. A little while later, I'm going to notice that that force of gravity has twisted the blue velocity vector to be here. But now, the force of gravity goes that way. Keeps pointing to the center of the story, right? Sometimes called the central force. Well, a little while later, this is actually about a week later from the beginning, we notice that the moon's now going this way. Again, force of gravity still pulling in towards the center. Still the only thing pulling it in towards the center. And about a week later, you're here, and 1 week later, you're there, and then by the time a month has gone by, roughly a month, you're doing the whole thing all over again. So what's the key thing to grab from this picture? The only force out there, the only force is this force of gravity, and it's towards the center, so we're going to call it positive. When we go to do F net equals ma, we're going to put force of gravity in for F net. And then we'll do our usual game of whatever A is handy. Maybe the V squared over R, or perhaps the 4 pi squared R over T squared version. A couple key points before we leave this page. Again, gravity is the only force in the story. That gravity force, the only one that's there, is perpendicular to the way that that moon is going. Small lie, we'll fix it next day. So since that force is perpendicular to the velocity, it's kind of like pushing on the driver's door of a car as it goes down the road. If you push on the driver's door, you won't make the car go faster or slower, you'll just turn it. And as long as you keep pushing in on the driver's door, all you can do is turn the car and not speed it up or slow it down. You know, to speed a car up or slow it down, you'd have to grab one of the bumpers and pull them forward or backward. And this force of gravity in this picture here just doesn't do that. So the acceleration caused by that force is not in line with the velocity. It's perpendicular to it, and that means the speed is just going to be nice and constant. Again, small lie, we'll fix it next day, but for a circular orbit, it's true the speed would not increase or decrease. So as we look at it here, it seems to be just a nice application of circular motion from Physics 12. Okay, don't copy this. This is just something I like to show the class. We'll just stare at it. It's from an old provincial exam, and it's not worth copying. It's just better just to look at. It says a satellite moves at a constant speed in a circular path, and the test question said, which direction represents the velocity of the object right now? Which way is it going? So I'll let you think about that for a second. And the way that it's going, well, it's going around the circle. And so if it's going around the circle, you should have said the correct answer is 2. 2 is the way that it's going. Here's a different question for the same picture. Okay, so still the satellite, constant speed, circular path. Which direction represents the acceleration of the object right now? Which way is it accelerating? Well, it will accelerate in the direction of the net force. And there's only one force making the net force. It's gravity, in towards the Earth, in towards that central body that's there. So that would be 4 for the direction of the acceleration, in towards the center of the circle. All right, for orbits, it's actually nice because there are only 2 possibilities for the math. Now you can choose whether you want to write FC or F net. Usually I actually write F net. But for that force on the left, The only thing you can put in there is gravity. It's the only force out there. And you may choose to put in an acceleration version with velocity, or you may choose to put an acceleration version in with period. And these are the results. Okay, so we've got force of gravity on the left, and then m times either v squared over r, or m times 4 pi squared r all over t squared. Now, for that force of gravity, don't go with mg, because we're probably pretty far up into the sky, and that won't be easy to calculate. Instead, go with the classic version, big G, mass of the thing in the middle that you're going around, maybe that's the Earth, mass of the little thing, that could be the moon, all over the size of that distance center to center squared. So we get to here, and now we can start looking at how we can clean these two stories up. These are the only two stories we will ever do for orbits, so they're probably worth some cleaning. And one of the things I notice is that the little mass, which is the mass that's circulating, right? That would be the moon if you're looking at the Earth-Moon story. That mass doesn't matter. It just goes away. Okay, so it's worth a little note here. The mass of the satellite, the circulating thing, does not matter at all. The capital M is the heavier thing. Okay, and in astronomy, we're going to call that the central body. Okay, if you're looking at the Earth and the moon, the Earth would be the capital M, and the moon would be the little one. But if you want to look at the Earth and the sun, well, the sun is in the middle. It's the big heavy M, the big M. And then the Earth would be the little mass that doesn't matter. So you have to think about which one's in the middle and which one's doing the circulating. Okay, cleaning these things up. The little m's are gone, and you can get to here. Now, there are some classic ways that physicists like to leave these two equations. I mean, you could leave them just as they are, but physicists like to clean them up and rearrange them a little bit. The one on the left, you can reduce the r slightly by multiplying by r. And then at that point, you'll have the v squared all by itself, and most people say, you might as well solve for v, take a square root. The one on the right, for reasons we're going to see in the next lesson, physicists often like to rearrange it pretty aggressively until the one on the right looks like this. So those are the two most common arrangements of F equals ma for planet orbits. They might even be worth just, penciling in on your formula sheet, because we will use them so often. The big M is the mass of the big heavy thing in the middle. It is not the mass of the little one doing the orbiting. That mass doesn't matter. Only the big one in the middle does. The r is the size of the orbit, and capital T is how long it takes to go around, and little v is the velocity for it. So let's maybe try one of each of those out, and then we're going to talk about one last thing. So here's the first one. And I should tell you that pretty much everything that can go wrong with this one is set up to happen. So it says find the speed necessary for a satellite orbiting at an altitude. You're going to learn to dislike this word altitude. Other words that are sort of synonymous with that, and they might say it's 500 kilometers, above the Earth's surface, or they might say it's at a height of 500 kilometers. Okay, the problem is this 500 kilometers is here, where that little green arrow is that I've got, and it's not the actual radius for the circular path. You can see that black dotted line actually has a radius that would end up penetrating right down into the center of the Earth. That is a big problem. So on times when people say, hey, I'd like to tell you the radius of the orbit, great, that's exactly what you want. Take their number and go. But if they offer you a number and say, oh, this is the height, or this is the altitude, or this is how much it is above the Earth, you're going to have to do this. You're going to have to add on that thickness for the Earth's radius to the distance you are above the Earth in order to truly know what the radius is for that orbit. Okay, so if I do that in this story here, what I can see is the radius is actually 6.88, 10 to the 6. Now, you're going to see a lot of questions where they actually do offer you the radius, and you'll see that word radius. If they say, yep, here it is, it's the radius, just take it and go. Don't add anything to it. But if they do say above or height or altitude, then you got to add. Okay, we're looking for speed. As I go back in the notes, well, I can see the speed versions on the lower left there. So I'm going to use that. If I get stuck and I'm like, oh, I can't remember it, you can always create it again just with F equals ma. That's all I did. So I'll just kind of go over this again because I wanted to emphasize that you would not want to put in mg because you don't know what the value for the Earth's gravity field is up at that 500 kilometers up. It won't be 9.80 anymore. So there's no easy way out here. You would have to go back to this version, big G, mass of the Earth, mass of your satellite, all divided by r squared. And that simplifies. You can cancel a little m, you can reduce an r, take a square root, and you get to there. So if you remember this, it's great. But if you don't, you can always make it. Now, throwing the numbers in, I put in big G, 6.67, 10 to the negative 11, put in the mass of the Earth, and I divided by that 6.88 number, 10 to the 6, and I took a square root, and I found this value. That's huge, right? Like, look at this, 7.6 thousand meters per second. So that's 7.6 kilometers every second. So it's really got to be going fast to be in that nice circular orbit. Okay, well, there's one where we practiced using that equation, right? The square root of gm over r to find the velocity. Let's try a different one out. Let's see if we can find the time it takes for the moon to do its orbit around us. Now that number is actually right on the formula sheet, but let's pretend that one number got, I don't know, obliterated by a coffee stain, and you're trying to calculate it. We do know the radius for the moon's path around us. That's the radius for its circle as it goes around us. It's not the size of the moon, but the size of its orbit. And we'll need to know the mass of the big heavy thing it's going around, and that is us. So we're good to go. If you get stuck and you cannot remember the equation, I just want to point out, you can always make it. You could say, okay, force of gravity is equal to mass times the acceleration. You can cancel a little m, which would be the moon in this case, and then you can rearrange it until you get to here. This rearrangement there is the most common for a reason we'll see in the next lesson. And at this point, it is just plug and play. We have all the numbers we need, including this constant that's one number for the whole universe. And then we can go and solve for t. We'll actually end up solving for t squared first, just by doing a little cross multiplying. And then we can take a square root. So the whole thing happens pretty quick, right? Get this 5.6 times 10 to the 12 for t squared, and one square root later, and you're there. And so there's the time. Pretty much matches up what's on the formula sheet. 2.37, 10 to this 2.37 million seconds, which is about a month. Okay? It's around 28 days or so for the moon to go all the way around us. All right, we're going to look at one more situation here and pick up a little bit of vocab along the way. We're going to look at something called synchronous orbits. But when we do that, you're going to see me use a number on the formula sheet that might surprise you a little bit. So we should go here first. A little astronomy trivia for you. How long is one day on the Earth? Turns out it's kind of a complicated question because there are different kinds of days. And you might be thinking, well, come on, 24 hours, 60 minutes in an hour, 60 seconds in a minute. Should be able to multiply all that out pretty fast. And you get like 86,400. However, that's not the only kind of day out there. That would be what we call a solar day, measured noon to noon, using the sun as a reference point. But if you use stars as a reference point, you can get a sidereal day, as we call it, and it's a little bit different. So one rotation of the Earth is this sidereal day, and it's actually about 4 minutes short. It's 23 hours, 56 minutes, and 4 seconds. I want to show you why. Okay, so I'm just going to show you a little picture here. The reason why I wanted to just generally talk to you about this trivia is if you look on the formula sheet, you will see that I have 8.62 times 10 to the 4 seconds. And you may have been expecting 8.64. For the work that we're going to do, you won't really notice a difference. And I would probably mark any question right, whether you used 8.64 or 8.62. But just so you can sleep well at night knowing that the formula sheet's not wrong, here's what's happening. Not to scale. Here's the Earth trying to go around the sun. And maybe you go and stick a big giant stick in the ground so that you can see when noon is going to happen, when it exactly points at the sun. And so if you're thinking, okay, well, yeah, one day later, I'll have that stick pointing at the sun again. Well, okay, is that the noon to noon time or the one rotation time? Well, in one rotation, you can actually get the Earth to go all the way around once, but it walks in its orbit a little bit during its year-long trip around the sun. So yes, it's actually gone in this story here all the way around once like this, right? And it's ended up pointing like that. But it's not pointing back at the sun yet because it's done a portion of its journey around the sun. And it needs another 4 minutes to do this, to go and finally point back at the sun. So just to spin once around is 23 hours, 56 minutes, and about 4 seconds. and then 24 hours is to actually get you pointed back at the sun. Wow, that means that one rotation is not really quite what you thought. It's not 24 hours, but a little bit less. Okay, well, with that in mind, let's look at the last deal of the day, something called synchronous orbits. If you look at satellite TV, you might have a dish on your house that's tracking or looking at a satellite that's sending out TV signals, and it's not actually moving. It's not tracking with motors. It's just sitting in one spot, which surprises me, right? Because I'd be thinking it would be like this, okay, my little goofy animation. As the satellite goes by, you would think that the dish would have to bend, but it doesn't, and here's the reason why. With synchronous orbits, there is one place in space, one distance from the Earth, where if you get your math right, it turns out that that little satellite with its TV signal, that's the thing in green, as it goes once around, if you get your timing right, the Earth will spin once around as well. So you have to make sure these synchronous satellites are going the right way, kind of matching the spinning of the Earth. They are definitely going around, but they're going around once every time the Earth does. So that's what a synchronous orbit means. It means that the orbital period matches the planet it's going around. Well, for us, that'd be the Earth. So you want to get this thing to go around once every, I almost said 24 hours, right? I guess it's once every 23 hours and 56 minutes and 4 seconds. There's only one place in space where that happens. Let's see if we can figure out where it is. So I'm going to see if I can find that radius, that one location. I'm going to use this equation here. We've only got two versions. I'm going to use this one to figure out where that orbit's located. And I'm going to put in one rotation time for capital T. I'm going to put in the mass of the Earth. And so that ends up looking like this. It's some cross multiplying. You're going to end up solving for r cubed. Then you can take a cube root and find the value for r. So the only place where this works is 4.22, 10 to the 7 meters out. That is very far out. Okay, really, really far out. In terms of like Earth sizes, that's like, I don't know, 6 or 7 Earth radii out there. It's quite a ways out. There's only one speed that works as well. Okay, you can use this equation to find the one speed that that satellite would have to be at in order for it to be perfectly in a circular orbit there. And it's around 3 kilometers per second, 3.07 times 10 to the 3 meters per second. It's a very far out orbit. And we've just figured out where it is and how fast it's going. Okay, I want to show you some pictures I grabbed from the NASA website showing some like locations of satellites so you can see how many satellites there are out there. Here's one. These satellites are all represented by little pixels, little white dots, and those are not geosynchronous. Those are just low Earth orbit satellites. They go around about every 90 minutes. If you go way out, zoom out quite a ways, then you'll notice that there's definitely a very popular place out here. You can see there are many, many satellites out here that are positioned in a place where they will go once around every 24 hours. Okay, so there's definitely some popularity in that place right there. So that's what a synchronous orbit's all about. And that's the last thing that we're going to take a look at for today.